Okay, these are pace notes for assignment 3. You are being asked to do some calculations later on. And the calculations are the calculations to talk about what is the entry pressure to get TCE out of the leaking drum into an aquifer, to do it for gasoline, and to also calculate something about the saturation profiles as you go down within the system. And so for all of these, you'll realize that you need to be able to calculate the capillary pressure versus saturation curves. From data as a function of saturation. And if you have these capillary pressure versus saturation curves, then you should be able to use these to calculate for any given capillary pressure what the appropriate magnitude of saturation at that particular depth is. So each of these saturation profiles you can get from this. The twist, I suppose, is that you only have information in this particular example for capillary pressure versus saturation for the behavior with one fluid. And the one fluid in this particular case is TCE. And so you can calculate the capillary pressure versus saturation curve for TCE, and then you want to be able to transform it to also use it for gasoline. So those are the two parts. So what do you need to do? You need to be able to calculate the capillary pressure curve by realizing that as you increase from the situation where you have initially water saturated, so you're initially at this point with zero pressure, and as you increase the pressure, let me draw it here actually, it'd be much easier. If you increase the TCE pressure from 0 capillary pressure, 1, 0, saturation of water, capillary pressure is equal to the non-wetting pressure minus the water pressure. Water pressure stays at atmospheric, so this is actually the capillary pressure. So as you increase the capillary pressure from 0, there's initially no water expelled from the system. At 0.5 kilonewtons, there's no fluid expelled. At 1, there's none. So this would be 0, 0.5, 1, and even 1.5. So you know that at 1.5, the saturation has to be still 100% water. As you go up to 2, all of a sudden you expel some water, initially a small amount, and progressively a larger amount. And so at 1.6, all of a sudden you end up with this point here, which represents this. As you increase the pressure to 2, then you expel some more fluid, ultimately this. So you go across here. And so incrementally, you end up being able to create these points. These points, if you join them, basically represent the drying curve. And on the way down, you create the imbibition curve in the same way. So you're able to do that. So the only wrinkle is that you have to convert these cumulative volumes expelled in milliliters into saturations. And so we know that the volume of water is equal to the volume of the sample multiplied by porosity multiplied by saturation. This is the amount of water that's in the sample, these particular saturations. So if you know the volume of the sample from core dimensions, if you know the porosity, which is equal to the volume of voids over the volume total. This is the volume total. And so we have this. So the volume of voids, when it's 100% saturated at the beginning of the experiment, the volume of voids is given by the weight of the core saturated, the weight of the core dry. The difference between these must be the mass of the water. If you know the density of water, you can calculate the volume of water, which is the last part you need to get the porosity from the volume of water of the volume total. So you're able to get a saturation from the volume of water. Once you have the saturations, then you're able to get everything to be able to complete this graph for TCE. Once you have this graph for TCE, you'd like to be able to convert it to be for gasoline. And to be able to do that, you need to be able to make use of the fact that the Capri curves all overplot each other if you realize that they behave with the same Leverett functions, which you presumably know for this. You know the porosity. You may or may not know the permeability. I think you don't know the permeability. You don't need the permeability. But you need to know that the permeabilities excuse me, of both cores, they're the same core, has to be the same. You know the differences in the different interfacial tensions for gas and water and TCE. And so you know these values. And so since you know that this value of J at invasion has to be the same number, it's about 0.3 we know, then you can calculate what PC0 would be for bubbling for gas relative to what you know, it's 1.6, right, or 1.55 kPa for TCE. And so based on that, you can scale these two plots. One will just be stretched relative to the other. Okay. And so once you have that, you have the two appropriate curves available, and then you can use those to represent the behavior in the below the water table in terms of capillary pressures versus depths, where you have the two different fluids, one for water, one for TCE, which is denser than water, and then you have to wonder, I guess, what you do with the gasoline. And so you can calculate these saturation versus depth curves for each of these. So that's basically the idea. So I'll leave it at that. Thanks.